some animations. I hope it's clear to you how does gas turbines for aircraft propulsion works. And I'm going to continue now. So as we mentioned last time, it goes first to a diffuser part, then the what we call the gas generator, and then we have the nozzle. So this is, we have already studied this part, which is the compressor, combustor, and turbine, and we deal with it exactly the same as before, how to get the properties, how to get the temperatures. Now we're just adding the diffuser and a nozzle. Of course, the nozzle is essential here because this will give us here the thrust or the high velocity to move the engine. We are concerned about two things here. First of all, the question will ask about what's V5. We are not going to ask about the power now. We're not going to ask about the efficiency, but we are concerning about the velocity. When you go to a plane, to an aircraft, you are interested when are you going to arrive there, and this is related to the velocity. Okay, so this is the important part. So the question is calculate V5. The second point here is that one feature of this gas turbine here, that the turbine only runs the compressor. In the previous part, stationary gas turbine, part of the turbine work, which you mentioned as 40% goes to the compressor and 60% goes to the generator. Now we do not have a generator here, and therefore the turbine work is equal to the compressor work. So remember that turbine work is equal to compressor work because this is just a shaft and they are connected together, nothing else. And therefore, this has to be satisfied here that the compressor work will be the same as the turbine work. We will come to that. Okay. So now this is again, here's the gas turbine. And let us see here as an animation. So first it goes to a diffuser. And in the diffuser, we utilize this velocity here because the plane is going this direction and here is stagnant air. But you are inside the engine here, you see that there is a velocity of the air coming in. This velocity is the aircraft velocity. While this is going this way, it looks like that if you are inside or the compressor here, we'll see that air is coming in with this velocity. And therefore, we change this velocity in the diffuser to a pressure. So the inlet to the diffuser at state A, then we change the kinetic energy to pressure, and therefore the pressure increases to 1. And the advantage of this here, you have to compress less now. By considering the diffuser here, now we can see here that the work for compressor will be less. And therefore we utilize this factor here. So this is a function of the diffuser to change the kinetic energy to pressurize, and therefore we reduce the compressor work. Then after that, it goes to the compressor 1 to 2, similar exactly to what we have done earlier. Then it goes from 2 to 3 here in the combustion chamber. The temperature increases from 2 to 3, and then 3 to 4. Now listen to that here. Normally 3 is given to us. So now we have 1, the compressor ratio is given, so I can reach 2. Now T3 is normally given as 1100 Kelvin or something like that. Then this expands here. Expands to what here? How do we get state 4? If you want to get state 5, this is different here. You have temperature over temperature equal pressure over pressure to the K minus 1 over K. But 3 to 4 here, we need to have the work here for the turbine is the same as the compressor here. So the way to get T4 is you say T3 minus T4 is equal to T2 minus T1, or the work turbine is equal to the work of the compressor. So this is the way to get 4. We say T3 minus T4 is equal to T2 minus T1. T2 is known, 1 is known, then 3 is given, then we calculate 4. Then from 4 to 5, this is expansion in the nozzle here. Once I get 4, then we apply the energy equation for the nozzle, and from 4 to 5, we get the velocity at 5, and this is what will be the question about that. Let me repeat this again. Here we have the diffuser. The air goes at state A with a velocity VA. We want to drop this velocity such that we increase the pressure. So we apply the energy equation for the diffuser. We will come to that, and then calculate from here T1. Then in the compressor, from 1 to 2, this is compression in the compressor, similar to what we have done in the stationary gas turbine. Then T3 is normally given, and therefore we move here at constant pressure heat addition from 2 to 3. Then it expands in the turbine. What limits this expansion? The expansion here is to give us very important thing here, that T turbine, it should run the compressor, and that nothing more than that. So we say here that W turbine is equal to W compressor. W compressor is well known now. Then from this we can get T4. As we reach T4, then we apply the energy equation for the nozzle and get V5. V5, this is the question required. Then we can calculate the thrust. The thrust here, the thrust is the force to push the plane in this direction, is the difference between V5 and VA. So V5 minus VA, this will give us the thrust or the force which pushes the engine in this direction. Okay, any questions so far? I will come to analysis, and I have an example, but just the physics with, I wanted to know that. So we have introduced two things now. V5, this is the question here. The question will ask about V5. This is the main thing here. And the second point here is that, remember here that the turbine does not have a generator here. So the turbine just runs the compressor. And therefore, there's a fact here that H2 minus H1 is equal to H3 minus H4. We do not say this is the problem. But once we say it's an aircraft propulsion, means that turbine work is equal to compressor work, and this is the only way to get T4. Okay. So now
Doctor,
second, yeah, sure, please go ahead.
There is no need to calculate the enthalpies once the temperatures are calculated, right?
Okay, it's a good question here. Okay, originally, the truth is that, or the accurate thing is that we calculate the answer. We say here H2, H1, H2, H3, H4. But when we say that Cp is constant, this is an assumption, we can consider temperature here. So we start from the enthalpy. Okay, so it is here when I say H3 minus H4 equal to H2 minus H1. It's wrong to say delta T is equal to delta T unless I say that Cp is constant. So for the case Cp is constant, you can say T3 minus T4, T2 minus T1. So the answer to your question, it is we must calculate the enthalpy unless we assume that Cp is constant, then we do not have to calculate the enthalpy. All right? Okay, thank you. So the second, okay, let me go back again here. So the first step here is through the diffuser from A to 1. Then the second is through the compressor to state 2. The third process is through the combustion chamber, heat addition at constant temperature. And then the next step here is expansion in the turbine, and just to make sure that you have the same work to provide to the compressor. Then the last one is expansion in the nozzle, where this will give us the velocity at V5. All right. So now let us go to the analysis now. Okay. When we talk about the nozzle and diffuser, this is the general equation. Okay, this is the general equation for any steady state. Steady state means that the rate of increase of energy is 0, and then Q minus W plus this term. So now for a diffuser or a nozzle, we do not have any work. We do not have heat addition, and also the size of it is not much, so we can neglect this part. So now what comes here, the work is 0. Also, the potential energy can be neglected, and normally Q is neglected, and therefore it remains that this. So for the diffuser and nozzle, this is here's the equation. Sigma HN minus H exit will be equal to V exit squared minus V inlet squared over 2. All right. So this is the equation for the nozzle and the diffuser. In the diffuser, we change the kinetic energy to enthalpy. In the nozzle, we change the enthalpy into velocity. So this term with the negative is equal to this term. So if I get this to the other side, so HE minus HE inlet will be equal to V inlet squared minus V exit squared over 2. Of course, we in this particular case here for the aircraft, we do not neglect this. In all other cases, turbines, all the previous chapters, all the coming chapters, this can be neglected. Except this is the only location here you cannot neglect that, because the velocity is very high and therefore cannot be neglected here. So we reach this equation. I'm sure that you know this equation from thermodynamics 1, and this is what we are going to apply here. Okay. Remember here that one thing here is that the enthalpy is in kilojoule per kilogram. When you calculate this will be in joule per kilogram, and therefore you should remember that there is 1,000 here. So write this as 2,000 if you use the velocity in meter per second. If the velocity in meter per second, enthalpy in kilojoule per kilogram, then this has to be 2,000. So for the diffuser, the inlet is at state A, as we mentioned earlier, and the exit at state 1. So apply this equation here. And accordingly, the enthalpy HA minus H1 will be equal to the change in kinetic energy. What is known here is that this H air, this at the inlet, this is the atmospheric condition. So this will be the pressure, of course, will be less than 100 kilopascal because up there the pressure is less, and the temperature also will be less than 300 Kelvin, but this should be given in the problem. Then H1, this is required here. The velocity at A, this is the inlet to the diffuser, and this is exactly the same as the aircraft velocity. So we have this is given, and V1 we normally neglect this, so it is not zero, but it is neglected with respect to VA, so this would be dropped. Okay, then we have, this is the equation here. This is given here, the conditions here at atmospheric conditions, this is given to us. The velocity, this will be given, which is the velocity of the plane. Actually, this is the velocity of the air going here. But relatively, it is stagnant, in fact. I mean, when you are in the plane here and you are moving in this direction, means that this velocity is atmospheric, it is stagnant here. But with respect to the diffuser, it is like velocity inlet in this direction. So this is given in the problem. So what you need here to calculate H1. So now with this equation, we come to calculate H1. Okay. So now we say that H1, this is what's required at the inlet of the compressor, is equal to HA, which are the conditions here at the atmospheric, and then this is the velocity of the plane or the velocity of the air coming into the nozzle. So this is what we have here. As the previous question you asked me, now this you have to make it like that unless the problem or you assume that CP is constant. If CP is constant, you can say this T1 is equal to TA plus V squared over 2. If it is variable, then you have to get this from the table. So you go at the temperature in the table, you get this from the table, and then you have the velocity here, and then you get H1, the enthalpy at the end. All right. So with this here, when we go to the nozzle, okay, let me just go back a little bit here, just to tell you here what do we want from that. Remember here, remember this figure here. From 1, 2, 3, 4, we learned this before. So we can do the same as we have done. But now I want to tackle how do you move from A to 1 and how do you move from 4 to 5. And this is what I'm considering here. So now we consider here the diffuser, and we reach this equation here that we moved from state A, which is given, now to state 1. So now 1 is known. So I can go to the compressor and get H2. Can go to the combustion chamber and go to 3. And then by saying that the turbine work is equal to compressor work, I can go to 4. Now I'm going to the nozzle now. The nozzle applies the same equation. It is the same equation. So inlet here is H4, with the velocity is neglected, and then 5 at the exit of the plane. This is the high velocity I'm looking for. So apply this equation. H4 will be calculated, and then H4 will be calculated, and then we have from this equation we get the velocity. Okay. And then of course HE, this will be at the exit of the turbine of the nozzle, and this is the atmospheric conditions at temperature 5, and then we will get that, and therefore from this equation you get the velocity Vx. Okay, so now I apply the same equation here, and from this here the velocity will be neglected at inlet, and from this equation we get V5. So H4 will be calculated, H5 will be calculated, and therefore we get here V5 from that. And this is the question. This is the most important part here in the aircraft. I want to calculate this velocity, and this what tells you which time you can arrive to your destination and so on. All right. So now we say here that H V5 will be equal to root mean square of 2 multiplied by H4 minus H5. We will have an example soon to see how to get that. But remember again here, if you do not multiply by 1,000 here, the velocity will come 2 digits, like an automobile. All right, so this is the problem. So if you get this at 30 meters per second or something like that, 2 digits, then remember right away that this is the velocity of an automobile. The velocity of an automobile, I know that you know this in kilometer per hour, but when you calculate it in meter per second, you are not familiar with that. And therefore, 120 kilometer per hour, which you are familiar with, is the velocity of the car, is equal to around 30 meters per second. So if you get this in 2 digits, 30 meter, 40 meter per second, remember here that this is an automobile, not an aeroplane. And what's the mistake here? That you forgot to add the 1,000 here, you add 3 digits here. Remember that V5 for an aeroplane, it has to be 3 digits, 300 meter per second, 350 meter per second, something. So it has to be more in 3 digits. This is V5. The error here, if you get these 2 digits, remember is that you forgot about 1,000 here. And I can challenge you that in any next exam, I'll find some students forgetting this and getting this as a car and pay millions of dollars to buy an aircraft, but at the end they will get a car, an automobile. All right. So this is here. The final thing that we want to calculate here is what we call the thrust. The thrust here is the mass flow rate multiplied by V exit minus V inlet. So this is the mass flow rate of the flow inside the nozzle here. What's the mass flow rate? Which is the same as the inlet because we're assuming air standard. So the mass flow in is equal multiplied by the velocity at exit minus the velocity at inlet. This will give you the mass flow rate. Remember that the velocity at inlet here is the same as the velocity of the plane because this is the relative velocity between the air and the compressor. And therefore, the compressor will see that there's a flow coming here, which is the velocity of the plane. So now the velocity of the plane will be given. Then you calculated V exit here at the exit of the nozzle. Then difference here multiplied by the mass flow rate. This will give you here is what we call the thrust, the force that will push the plane in this direction. So now we have the cycle is like that. We have 1. This is the inlet to the diffuser, then 2 at the exit at the inlet to the compressor. We get this 2 here from the energy balance on the diffuser. Then from 2 to 3 through the compressor, then 3 to 4. 4 to 5 is equal to 3 to 2. And therefore we get from this case, we get 5 here. Once we get 5, 6, we can get it through all the pressure ratio here. And therefore we can get the temperature or the enthalpy at 6. And then from this we get the velocity. So now let us go to, I think, an example here. Okay, so I'll go to the example, Shabab. Shabab.
Yes, doctor.
Yes.
Yes, yes.
Okay.
Yes, Dr.
So I'm going to any questions? Okay, so I'll go to the example, and this will give us numerically exactly what we need. So it says a jet engine operating on an ideal cycle. Ideal cycle means that these are isentropic process. The velocity at the nozzle exit, find the velocity at the nozzle exit and the thrust. So this is a question here. We don't ask you for power. We do not ask you for efficiency. The most important part here is the velocity V5 and the thrust required to push the plane. So it's giving us P1 and T1. So this is the atmospheric condition. You can see here that the pressure is less than atmosphere. When you are in a plane, the pressure is low and the temperature is also low, and it gives us the pressure ratio on the compressor. So this is here is given like that. He's just giving the diameter here. And okay, this is a turbine inlet temperature is giving us this temperature here. So now we have the data is given to us, P1 and T1, the compressor ratio, and the temperature at this point. This is the same as we were given earlier in in the gas turbine. We're given this point, pressure and temperature. We're given the compression ratio, compressor ratio, and then we are given the temperature at this point. And it's giving us the diameter for something else. We'll see this later. Okay. So now what we do here, I want to go from 1 to 2. Now we are not considering the diffuser here. So now we have the compressor, similar to the stationary gas turbine. So we say T2 over T1. Now I'm assuming here that Cp is constant. So T2 over T1 will be equal to R over K to the power K minus 1 over K, and this will give us the temperature at state 2. If I have a diffuser, then I will apply the equation for diffuser, and then one will be different here, and therefore the pressure ratio can apply it here, and this will save a lot of part of the energy for the compressor. Then we have T3 here. T3 is given, and then from this ratio here, I can get T5. All right. So now I see some students. I can see that 1 or 2 students in the next exam will say that this is T4. It's not correct. This is T5 here. T4, how do I get T4? By saying that the turbine work is equal to the compressor work. But now I'm getting that this applies here because RP from 1 to 2 and from 3 to 5, not 3 to 4. So now I can get T2 from this equation. I can get T5 from this equation again. Then I got how to get T4. This is a critical point here, and I can underline an error here that 2 students at least will make a mistake here for 4. They consider from 3 to 4, they apply this equation. This is not correct because the pressure ratio is not the same here. So how to get T4? By saying that the compressor work is the same as the turbine work. So now I say T3 minus T4 is equal to T2 minus T1, and therefore I get T4. Please remember this, Shabab. T4, you cannot get it from an equation like that. This is not correct. Because RP, the pressure ratio from here to there. But the thing here is that the turbine work is connected on a shaft with the compressor work. So the turbine work will be equal to the compressor work. Therefore, I apply this equation and get T4. So now T3 is given. From that, I get T5. T1 is given. From that, I get T2. T4, I get it from this equation here. So I have all the temperatures now given to us. This is the first step you do here. Once you have done this, then you can apply now the energy equation from 4 to 5, and then get V exit here, which is the velocity at exit here. So you can see here that V exit will be equal to 2Cp, and because this is here kilojoule per kilogram, he multiplies here by 1,000. Okay, and then you get the velocity here as 5,28500, 3 digits here. Remember that if you get these 2 digits, means that you are buying a car, an automobile, not an airplane. And the error here, I know you know it, but sometimes you forget it, that this is here because this is Cp in kilojoule per kilogram, K. This K is not an SI unit. Therefore, I have to multiply by 1,000 here. Right, Shabab? So I don't want to see here this less than 100. If you get this one less than 100, means that this is a car. And now what your boss will do with you if you send this and he gives you millions of dollars, and then the company will send you a car which satisfies the velocity of 30 meters per second here. Can anyone tell me what the boss will do with you?
Fire you.
Cut his
So
throat.
what? Huh? Okay, so what should I do if I get this in an exam? What's your advice? If a student calculates the velocity here as 40 meters per second like an automobile, what should I do?
If he
They
has a
should
time
write
to
at
change
least
it, he will change
there
it.
is a
If
mistake.
there is no time, he should write no.
Right. Okay, so please remember this. I'm just raising this point to remind you that please remember the 3 digits here. 1, 2, 3. This is an airplane. If this is only 2, then this is an automobile. All right. Once we calculate this, then now he is giving us the velocity of the plane. So now we apply this equation. It's giving us the area. So it has given us the diameter here. So pi over 4 d square multiplied by the velocity. This will give us the mass flow rate. So this is just to calculate the mass flow rate. Once you have the mass flow rate, then the thrust will be equal to m dot v exit, which you calculated, minus v inlet. V inlet is the same as the velocity of the aircraft. Remember here, the velocity of this is the velocity of the aircraft, and this is the velocity of the gases outside. These are not the same. Of course, this has to be more than that, such that this is the force. This is the driving force for the aircraft. The velocity of the gases out, which is this one, minus the velocity of the gases in. The velocity of the gases in is the same as the velocity of the plane. Okay, so with this here, you get this is the amount of force required to move the automobile. Okay, so this is here is a problem. If you want to repeat the problem again, I can do that. If it is clear, then I'll go ahead. I just wanted to tell you here that we have the quiz on 25. It is up to this point. This is included in the quiz. All right, but this part, what I mentioned all today, is not included in the midterm. Is it clear, Shabab?
Yes, clear.
Okay, I'm giving a problem on the multiple choice questions on how do you calculate the thrust here. But in the midterm, this what I mentioned today, all what I have today regarding the aircraft is not given in the midterm. All right. Okay, Shabab, questions here. Do you want me to read the example again? I can, no problem with me. But yes, go ahead.
Can you repeat what you said about the question, the quiz?
Yeah, the quiz will come up to this point. Okay, I have a question on how to calculate the thrust on the quiz. But in the midterm, the aircraft is not included.
Oh.
Okay, so yeah. In the midterm, the aircraft is not included. It is included in the quiz. خلاص شباب, clear?
Clear,
Yes,
inshallah.
clear.
Okay. But this is what we'll do with this. This is ends my this chapter here. I have another example on the regenerative Brayton cycle. This part is required for the midterm. So this is here. I'm giving an example on the regenerative Brayton cycle. So this air says here, air enters the compressor of a regenerative gas turbine engine. So normally we have pressure and temperature given and compressed 2. So compressed 2 means it's giving us the compressor ratio is 8. The regenerator has an effectiveness of 65% and air enters at 1200 and then it goes here at is giving us the efficiency of turbine and compressor. Let me just explain it here. So this is the diagram. Is giving us P1 and T1. Is giving us the compressor ratio, and is giving us this temperature here, and it's giving us the effectiveness or the efficiency of the regenerator. So now I go back. So now remember this cycle here. So we have 1, 2, 3, 4, and let us go and see what's given here. So it's giving us P1 and T1. Is giving us the pressure ratio is 100 to 800, so it's 8. Is giving us T3 is 1200 Kelvin, and is giving us the regenerator effectiveness 65%. Is giving us the isentropic efficiency for the compressor and for the turbine. Now, of course, it asks here what is the heat transfer in the regenerator, what is the thermal efficiency, and what is the back work ratio. And in this example, he wants to calculate this for different, for cycle with no regeneration or for a cycle with different efficiencies, it changes efficiency. We will only make it for one case, and then this is just repetitive here. You can repeat that. So I'm going here. This is the answers when you consider the different values for efficiency of the easy changing this value and getting results. I'm going to take only one value, and then this is just a repetition of the work. So now we'll go, this is it is systematic all the time. We are given P1 and T1, so we want to reach 2. So now we apply this equation, T2S over T1 is equal to P2 over P1 to the K minus 1 over K. This will give us T2S. So now we start here from 1, get T2S. Then we apply the compressor efficiency and then calculate T2A. So now we apply here the equation to get state 2A. So now with this here, we get 2S. Then forget about 2S. In your calculation, now we have 1 to 2A. This is the actual process. Okay, if any question at any point, please stop me. Okay, stop me and ask at any point. Then we have T2. Remember that T2S and T2A are more greater than T1. Okay, otherwise you would have flipped this value here. So this will what will call me the reason for getting 2 is less than T1. But remember here that T2 has to be more than T1. So now the first step is to move in the compressor from 1 to 2A through 2 steps. You get first 2S and then you move to 2A. Okay. Then you calculate W compressor, which is 2A minus T1, and therefore, because CP is if this is if CP is variable, then you have to get this from the chart. And in this case here, if you want to do this, if CP is variable, what you are going to apply here is that at T1 you get PR, and then you apply the equation that pressure ratio 8 is equal to PR2 over PR1. Then you go to the table and get PR2. And from PR2, then you calculate H2S. Then apply this equation without temperature here as this and calculate H2S. So the only difference here is that you go to the table through PR or you do not, or you assume it is CP constant. This is the only change. So now we have W compressor is equal to that. Then you go to the turbine now. T3, as I mentioned, normally is given in the problem. Okay. Then we have W turbine is equal to 3 minus 4. So I have to get here 4A. So we do the same as we have done earlier. So we'll go from 3 to 4S first, and then here get T4S. Once we get T4S, then we apply the efficiency of the turbine, and then from this value, then we can calculate 4S. I'm sure that you are quite expert now of how to move from 4S to 4A. Then you have now temperature T4A as this given here. Okay. Then once you have done that, you calculate W turbine. Remember here W turbine is 464. W compressor is 326. So the ratio is about 40% as we mentioned there. So the back work ratio is W compressor over W turbine. This is the value here, and over this value it gives us here 70%. Can you tell me why this is higher a little bit here? Because now the compressor is not isentropic, so the compressor work increases, and here the turbine work has been decreased because this is the efficiency of these two values here, and therefore the back work ratio is higher now. So when it is ideal, this will be less than that. When it is irreversible, the compressor work increases, turbine work decreases, and this will be more than that. However, this is a little bit in the higher side because it's giving us the efficiency of the turbine is low and the compressor is low. Therefore, I still stick to around 0.4 to 0.5. Okay, so this is the first part. Then it's giving us the regenerator. To calculate the efficiency, we need this. This is given to us, so I want to calculate T5 now. So we say here that T5 minus 2A. What's 2.5 minus 2A? This is the actual rise in the regenerator. Then over the maximum rise. What's the maximum rise? It is T4A minus T2A. Remember that this is the actual exit. I cannot use 4S now. This is T4A. This is the maximum I can go now is 4A. So 4A minus 2A, this is the ideal rise. This is the maximum I can go. And this is the actual. So this is here will give me from this equation, I get T5. Once I get T5, then I can go and calculate Qn. So now I can go now and calculate Q. He's asking for Q regenerator, so I can do that by Q regenerator is H2A. It's 5 minus 2A. This is a heat transfer in the regenerator, so we can calculate that. Then we can calculate, this is not much important, but he's asking in this question. But what's important to us here is how to calculate the heat addition from 5 to 3. He's also asking about T6. You can get T6 here by saying here that the change, the increase in the air here is equal to the loss in the enthalpy of the gases is equal to the increase in the air. So you can say here 4A minus 6 is equal to Q regenerator, which we have calculated earlier, which is equal to 5 minus 2A, then we can get T6. This is also not important to us here, but in the problem here, he asks for that. But now what's very important here is to calculate Qn. Qn is Cp T3 minus T5, or H3 minus H5. So now we calculate this and get the thermal efficiency here from W net. We calculate W net, and then we calculate the efficiency, which will come to be 27.4%. And this is the thing that I mentioned last time, that for a gas turbine, the efficiency is low. And this is why we use combined gas vapor cycle, which can raise this to 55%. Okay, so this is the end of what I want to say here. Is there any questions? Because I want to go to one slide. Okay, so let me go to one slide. It will take about 3-4 minutes, and then I can give some space for any general question. Okay, one thing I want to look at this slide. Can you see the slide? I give you 1 minute to study this. Can anyone read the title here and see what is this here? It says we in the previous chapters, what is our objective as engineers? As engineers, we were concerned about producing electrical energy, power. Shabab, are you still with me?
Yes.
Yes.
So I want you to talk now as engineers, not students. Huh? You are engineers now. You can see here that this is the map here for Saudi Arabia. This is we produce power from so many things, from steam turbines, from diesel generators, from gas turbine, from desalination plants, from combined cycle. So if you look at this here, this is steam turbine. The chapter 8, you learn it from chapter 8, how do you get 40% of the electrical energy in the kingdom? So you are expert now in producing 40% of the electrical energy in Saudi Arabia. In chapter 9, you learned more about 39% here. And also in chapter 9, you learned more about the diesel engine. I'm not talking about transportation now. I'm talking about the energy that sometimes we use the diesel engine in plants to produce some electricity for emergency, so on. So now you learn it from chapter 8 and chapter 9, 39 plus 1, 40 plus 40. So this is 80% of the power produced in the kingdom. So you are expert now of the production of 80% of the power in Saudi Arabia. Also, we have this combined cycle here. You learned about this as well. So this is 7%. So you are aware now of 87% of the production in Saudi Arabia. All right, Shabab?
Yes.
Yes, doctor.
So this is our objective, and you are expert now of producing 87% of the energy, of the electrical energy from fossil fuel in Saudi Arabia. Then we have others here, 3%, maybe this renewable or something like that. And then, of course, the desalination plant have 10%. But 87% depends on chapter 8 and 9. And this is why we say that these two chapters are very, very important in this case. Now we produced a lot of power, and now we want to use this power, right? Okay, so now let us see here that how is this power distributed? Okay, in the kingdom. So we produced the power, electrical power, through either steam turbines, gas turbines, combined cycle, or others. Now we are going to use this energy. You see, this is the residential here. This is where we live. This is air conditioning, refrigerators, and so on. So we will have two chapters. In the next chapter, we will consider refrigerators, and one chapter later on, we will consider air conditioning. And this use 50% of the power that we produced in the previous two chapters. There's some others commercial here, The government locations, buildings and so on use 16%, and industry use 23%, but the major part is goes to the residential, particularly the air conditioning. Air conditioning uses 45% of the energy produced. Okay, I'll stop at this point, Shabab. And next time, since we produced a lot of power, we are rich now of electrical energy, we will go and use it in the refrigeration cycle. So this will be our next chapter. I'll start this, inshallah, next class. Okay, any questions regarding concerned about exams and so on? I found just one thing. I found that some students have a class, a regular class from 5:20. So I discussed with my colleagues and we'll confirm it today that we'll make the midterm 6:30 on the same day, 26. Okay, so we'll move it from 5:30 to 6:30. Anyone having a class at 6:30, regular class? So is that okay with you?
Yes.
Okay, خلاص, it will be 6:30. I'm sorry to change that, but I have only a couple of students or so. I don't want them to lose their class, and the other, and this is not allowed also to make this in the same time of the class. I was wondering that there's no classes after 5:30, but it happened. So we change it to 6:30, inshallah, on 26, as we have earlier. And the quiz will be for 20 minutes, and this is Sunday before the midterm. And prepare any questions. If you want me to solve a problem, then just send me the problem number before that. So I utilize 20 minutes of the class on Sunday, and then the rest of that I will answer your question, give examples, whatever you want from me. But I'm sorry. Okay. On Tuesday and Thursday we will have next chapter. Next Sunday we'll have a quiz. The quiz will be for 20 minutes. It's MCQ questions, and then after I will take only 20 minutes of the class. The rest of the class, I will have discussions on the midterm exam, any questions you have, any problems you want me to solve. So this will be for your benefit.
Victor,
Yes, please.
can I suggest you a question?
Can you what?
Can I suggest you a question?
You suggest a question?
No, not a question, an idea. How about if you put the next lecture for as a whole session to solve an old exam question?
This is what I'm going to do on Thursday, on Sunday.
On Sunday,
On Sunday, okay, I don't mind. I can have half an hour or so. If you send me, who's I'm talking to?
Ali Haji.
Okay, Ali, can you send me what part you want, or send me a couple of problems that I solve? I mean, just give me a guide, because for everything is for me the same. So so if you find something difficult, any problem that you face, then send me the problem. Then I can solve it either next class or on Thursday.
Inshallah.
In addition to Sunday. All right, Ali? Okay, so I'll expect something from you. Which part I have to give help session on, or even you can give me the problem. I can talk about it. Yeah, I can solve. Okay, Ali. Any others?
If you have an old exam problem, it's better than the question asked.
I'll send you some old exams on chapter 8 and 9. I will do that. Inshallah. Any other issues, Shabab?
دكتور
Okay, can I just just give me a minute, I take attendance. So if anyone wants to leave, and then I'm staying with you, but just so I do not forget that. Just 1 minute, okay. Okay, خلاص, I took the attendance. If you want to leave, you can leave. I'm staying with you if you have any question. Please go ahead and ask. The question, please ask.
دكتور
دكتور
السلام عليكم.
عليكم السلام ورحمة الله.
تفضل انا بعدك.
ما تقصر. دكتور بالنسبه للاتندنس انا قطع عندي هذه الدقيقه بس ورجعت، فما ادري اسمي كان موجود ولا لا.
أنا لسه واخده من دقيقة واحدة بس.
ايوه انا قطع والله تو بس.
طيب خلاص.
فما...
Just I cannot check now. Just send me your name and I will include it.
اوكي ثانك يو.
Just send by email your name and then I will include it. Okay.
ان شاء الله. ثانك يو.
No problem. Thank you. Faisal, I believe you wanted to ask.
يس دكتور البرايتون سايكل عندنا السمبل ايديل ونن ايديل صح؟ الريجنريتيف ما هي معنا في المتر صحيح؟
صحيح regenerative مش موجودة في الميد تيرم. يس رايح.
خلاص برايتون اما حقة الفيبر سايكل معانا في المترم وفي غيره.
فيبر سايكل معانا في الترم. الفيبر سايكل ريجنريتيف اور ريهيت معانا في الميد تيرم، ولكن في بالنسبه لشابتر 9 regenerative reheat are not included, so only Brayton cycle ideal or non-ideal.
سمبل سايكلز صح؟
Simple cycle. Simple
Ah.
cycle. Very good. Simple cycle is.
ثانك يو.
Simple ideal or non-ideal. I may get it non-ideal, huh? طيب.
اوكي
Okay, فيصل. طيب
اوكي
اوكي.
ثانك يو.
Doctor, by an ideal, you mean you will give us the isentropic efficiencies?
Very correct. Yes, correct. I think the one there it has efficiencies. Yes, it is irreversible. As far as I remember, yeah. Any other questions, Shabab?
Thank you. Shall I leave?
Yes, please. I already took it, and you can leave. I'm just waiting if anyone have a question. Otherwise, you can leave.
Doctor, can I discuss with you the assignment during the office hours?
Yes, sure, no problem. Some students didn't done that, yeah.
Okay.
6:30 today, huh?
Inshallah.
Inshallah. If you don't find me, just send on the WhatsApp sometimes, because it is strange at 6:30, so I sometimes forget, yeah. So just send me on WhatsApp or give me a missed call, anything, I'll be with you. But I'm ready, and just قال من لا يسفي يعني.
Inshallah.
شكرا حسن، جزاك الله خير.
مع السلامة.
Okay, شباب, shall I leave? I'll count to 3. 1, 2, okay, 3. Okay, السلام عليكم. I'm leaving now. السلام عليكم.